Hello, class. Well, this is our last lecture. I may do some other thing where I actually send you out a short 3 or 5 minute video or something like that, just to talk to you by email. But this is going to be our last lecture as far as the material in the course goes. And what I want to do is I want to continue on with that last lecture that I had on the series / parallel circuit. And I'm just going to redraw that circuit here, right? We had a capacitor that was first, and then the resistor and the inductor in series. And then we had another resistor that was between points A and B, this being point A, and this being point B. And then we had a resistor and a capacitor in that branch of the circuit. And then we had an inductor and a resistor in that last one. And we actually had a frequency of 1000 hertz. And we figured out what all of these things were. This is C1 and C2. This was L1 and L2. This was R4, R3, R2, and R1. And I gave you all of those various different things. In fact, I'll give them to you again. The capacitors were both 159.16 nanofarad capacitors. L1 was 1.5916 millihenries, and L2 was 3.183 millihenries. And then what that did with the individual things is it really made them all either 100 or 200. And if we look at this circuit in that regard, you can see that R1 actually I should probably do it in these actual things here, but anyway, just going back to this, R1 was 100 plus J0 ohms. R2 was 200, 200 plus J0 ohms. R3 was 200 plus J0 ohms, and R4 was 100 plus J0 ohms. If we looked at the individual ones for C, if we C1, or I should say this should really be the impedance for all of these. So the impedance for those, because I'm writing them out as impedances, and why don't I write C1 out as impedance too? So 0 minus J 100 ohms. And that also equals C2. Where can I write that? It's equals C2. So anyway, and then if I'm looking at Z sub C for L1, L1 is 0 plus J 100 ohms, and Z for L2 would be 0 plus J 200 ohms. So that's what we have. We figured out a lot of things already. I'm just giving those to you to just sort of, bring you up to speed for the other one. We figured out what the total impedance was for the entire circuit coming out of the source, and this was a 100-volt peak source that we had there. And of course, that defines the reference angle too as 0, right? Everything is 0 degrees phase shift off the source. So we figured out what the total impedance was, and that was, and I'll write it in two different ways, that was 95.3 ohms at an angle of, and wouldn't you know it, didn't, oh yeah, minus 25 degrees. Or we could say that that was 86.36 minus J 40.03 ohms. We also found out what the current was. The current through the system was 1.05 amps peak at an angle of 25 degrees. I'll refer you to the last lecture that we had for you to see where that came from. Although you could probably do it yourself just by remembering that V equals IZ, and it says true, you know, with complex numbers as it is without complex numbers. And that's what we're going to see here today too, when we figure out what the voltage drops are for, you know, the voltage at A and everything else too, is complex numbers work just like any other numbers, don't they? I could also write this as a breakdown because that 1.05 is actually 0.95 plus J 0.44 amps peak, if you want it in the rectilinear form, and we may have to use that. So why not have it there anyway, right? Now, what I want to find in this lecture, and let's just write these down. I want to find V sub A, right? What's that? What's V sub A? What's V sub B? V sub B is right here. I've decided I'm not going to go with V sub D and do all of that, because really in showing you the first two, getting V sub A and getting V sub B, I think that that will be enough instruction for you to realize how I would go ahead and break down the currents at B and figure out what the current is going through here, because we'll already have done it twice. So I don't think we have to do it again. But we know what I is, and I'm going to call that I1, because I1, or I total, if you want to think of it in that regard, is the stuff that's flowing into the source and the stuff that's flowing out of the source. So that'll be I1. The next thing we've got to figure out is what is the current that's going through here? I could call that I2, and what, or actually I sub R1. Why don't we do that? Because we can differentiate between R1 and R2, because we also want to find the current that's flowing through R2, don't we? And we know what at the breakdown here, what this is. What is the impedance when I'm looking in this direction? We know that from the last lecture. And what's the impedance looking in this direction? And I think we know that too. And we also know the current, so we can figure out the voltage at A. So let's do that. Now, what we want to find out, we know what the voltage is on this side of the capacitor. What's the voltage on the other side of the capacitor? We know there's going to be that voltage drop supposedly across the capacitor, right? Isn't that what we do? We look at the voltage drop, and it's a complex voltage drop. It's not just going to be a real voltage drop. It'll be a real plus imaginary voltage drop. So what's my voltage drop across that first capacitor? And, you know, going back to Ohm's law, that's why I put a star next to those things. Going back to Ohm's law, V equals IZ, we can see that it's just going to be the current through there, which would be 1.05 amps peak at an angle of 25 degrees times the impedance of the capacitor, right? And the impedance of the capacitor, just the impedance of the capacitor, is 0 minus J100. Well, if I wanted to write that in phasor form, I could say it's 100 ohms at an angle of minus 90 degrees, because minus j, the minus j direction on my complex plane, and let's not forget the complex plane, right? My real numbers and my imaginary numbers, because minus 90 degrees is going to be down here, right? And isn't that where you've got it? Minus J1 over omega C. Isn't that what the reactance or the impedance of the capacitor is, right? So 100 ohms at minus 90 degrees. And so that's going to be my voltage drop across there. And so we want to find out, well, what's that going to be? Well, we can see 1.05 times 100, that should give me 105. So we started off with 100 and we're dropping 105? No, of course we're not, because we've got 25 and minus 90, don't we? So 25 minus 90 gives me minus 65. So 105 volts, but it's at minus 65. So let's turn that, you know, so delta voltage drop across C1 is going to be 105 volts at minus 65 degrees. And if we break that down into its rectilinear form, that's going to give us 44.4 volts minus J 95.2, right? So that's my voltage drop. Well, if that's my voltage drop, then what is my voltage at A going to be? Because my voltage at A is just 100 plus J0 volts minus 44.4 minus J 95.2 volts. You're probably saying, hey, there's a minus and a minus there. That's right, there's a minus and a minus there. So that makes it a plus, doesn't it? Thank you. Minus, or 100 minus 44.4 is 55.6. And then minus 0 minus a minus gives me plus J 95.2. And if you're wondering what that is, as a phasor, that is 110.2 volts at an angle of 59.7 degrees. All right. And we're going to need that again too. So, you know, want to keep that in there. Now that tells us, and you know, at this point here, we're saying to ourselves, okay, well, if that's true, if I've done everything right in the solution of this problem over the course of 2 lectures, right? If I've done everything right, which I have, I've checked it, then that tells me that I've gone from 100 volts here, and I've gone to 110 volts here, but there's a change in the phase shift angle, isn't there? And we know that that happens because remember the lecture I gave you on the voltage maker? You know, so we know voltage can go up and down. It's not limited by the source. We can make, with AC, we can make voltage. We can do it with DC too, but I'm just saying we can with AC. That's what we're talking about here. So there you go. That's our voltage at A. Now, the way I want to look at this is a check. This is where I want to check and see if everything that I'm doing really is right. I can actually figure out the current that's flowing through R1, right? I can figure it out one of 2 ways. Now that I know that voltage at A, I can take the voltage at A and find the voltage drop down here. In fact, I know the voltage drop, don't I? Because it goes from 110 volts at 59.7 degrees down to 0, right? This, let's not forget, is 0. That's ground. So if I know what the voltage drop is already, and I know what the impedance is of that, shouldn't I be able to find the current? And that's what I can do. Let's do that. Let's find the current through R1 that way. Now we're going to find it two different ways. We're going to find the current through R1 two different ways, and that's what I want you to see. So the first way that we're going to do it is we know what the voltage drop is, and I equals V over R, right? So we know that the voltage at A down to 0. So the voltage at A is 110.2 volts at an angle of 59.7 degrees, right? And we know what the impedance of that is because it's 100 ohms for R, 100 ohms for L1. So it's just 100 plus J100, isn't it? I'm not going to write it down that way, but 100 plus J100, I'll just write it here. 100 plus J1, 100, that's a 1, equals 141 at an angle of 45 degrees. And so that's what we've got, 141 ohms at an angle of 45 degrees. And so let's see what the current through that is supposed to be. And I think I've got it right here. Yes, I do. It's 0.78 amps. Oh, wait, I forgot to, no, that's right. Amps peak at an angle of 14.7 degrees. Okay, now we want to also keep that, in fact, I'm going to write it out in that regard, but I'm also going to write it out in its rectilinear form, 0.754 plus J 1.98, because we're going to need that again, right? And of course, those are peak amps. So we figured out what the current is going through R1, right? This way, because we know what the voltage drop is, and we know what the impedance. We're going to use that again someplace. All right. And you know, really, we're going to use the voltage at A too, but we'll leave that there for a while. I'm just going to put voltage at A here for your notes, so that you know that I am circling the voltage at A, and I guess the complex plane thing too. Anyway, now we found it that way, but let's find it another way too. Let's say that the current through, oh, you know, wait a second, I'm really sure. Yeah, we can do that. So the current through R